For the better part of a century, we've had this incredible secret weapon in medicine, antibiotics. They've made complex surgeries possible, childbirth way safer, and turned what used to be deadly infections into, well, just minor inconveniences. But that whole era of confidence, it's starting to fade. We are locked in an arms race with an enemy that's microscopic, that's totally relentless, and honestly, it's evolving a lot faster than we can keep up.
Okay, just take a look at this chart. It tells a really startling story. Way back in the 1940s with penicillin, it took decades before we saw widespread resistance. But now, look over to the right side of the chart. For our newer drugs, that window where the drug is actually effective is just slamming shut. We're talking resistance popping up in just a couple of years. The trend here is crystal clear. The bacteria are getting faster.
So that begs the really big question, right? What is going on here? Are bacteria just getting luckier, or have they fundamentally upgraded their playbook for beating our best drugs? Well, it turns out they have an unbelievably efficient way to learn and share their survival tricks.
To really get this, we've got to look at how bacteria trade information, because they have a system that gives them this massive evolutionary edge, and it lets them adapt at speeds that are, frankly, hard for us to even wrap our heads around. The secret sauce here is a process called horizontal gene transfer, or HGT for short. Now, unlike us, bacteria don't have to wait around for the next generation to inherit useful new traits. Nope, they can just pass genes directly to their neighbors, even if those neighbors are a totally different species. It's like the ultimate form of social or genetic networking. And this genetic superhighway has three main routes. First up, you've got transformation. That's where a bacterium basically just hoovers up loose DNA from its surroundings. Then there's transduction, where a virus acts like a little genetic delivery drone, carrying DNA from one bug to another. And finally, you have conjugation, which is the most direct method. Two bacteria literally connect to each other to hand off a piece of genetic code.
Yeah, you can really think of it as the biological version of swapping cheat codes to beat a super hard video game. And one of their favorite tools for packaging and sharing these codes is a special piece of genetics known as an integron. They're like a biological USB drive. They are literally built to capture and then use different genes, which are packaged in these little units called cassettes. And wouldn't you know it, these cassettes very often contain the instructions for antibiotic resistance. So the whole integron can then get passed from one bacterium to another, letting a pathogen pick up resistance to a bunch of different drugs all at once. So this insane adaptability makes bacteria a really, really tough opponent, which led some scientists to ask a pretty radical question. If bacteria are such masters of evolution, could we maybe use that exact strength against them? Could we actually turn their evolution into a trap? The idea was to engineer a situation where the bacteria's own evolutionary instinct would lead them right into a double bind. Basically, a scenario where any move they make is a losing one. It's an evolutionary checkmate. And this brilliant strategy is called collateral sensitivity. The whole concept is just genius. Instead of just trying to kill the bug, you force it to make a choice. To get resistance to drug A, the bacterium has to change its genetics in a way that, as an unavoidable side effect, makes it incredibly weak to drug B. You're designing an evolutionary trade-off. And this table right here illustrates just how promising this looked at first. These are lab results with real clinical strains of E. coli, and they showed this predictable network. When the bacteria evolved to resist one drug, ciprofloxacin, they reliably became super sensitive to other antibiotics. It looked like we finally had a roadmap to exploit their weaknesses. But in the evolutionary arms race, even the most cleverly designed traps can have escape hatches you didn't see coming. And it turned out the bacteria had one more move to play. So, in this really fascinating experiment, researchers took these specially evolved E. coli, the ones that were supposedly caught in the trap, and they just let them grow for 300 generations in a perfect, cozy environment with zero drugs. The question was pretty simple. How stable is this weakness? Is the trap going to hold over time? And the result was, honestly, it was stunning. After those 300 generations, that collateral sensitivity network, it had completely collapsed. The bacteria weren't extra vulnerable to the other drugs anymore. They had found a way to escape the trap, and they did it without any drugs pushing them to do it. So how on earth did they pull that off?
With no antibiotic pressure, what was the driving force that made them dismantle this evolutionary trap that scientists had so carefully laid out for them?
Well, the escape was kind of an accident, an unintended consequence of the bacteria just trying to improve themselves. See, it turns out that initial mutation for drug resistance, it came with a price. It had a high fitness cost, which means it made the bacteria grow slower. So over time, new compensatory mutations started popping up that fixed this growth problem. These new mutations help the bacteria get back to normal. But in doing so, they also accidentally erased the collateral sensitivity. They weren't trying to escape the trap. They were just trying to get back in shape. And this chart shows that comeback perfectly. The orange bars, that's the initial, really significant fitness cost of being resistant. But look at the purple bars. That's after 300 generations of evolution. In almost every single case, the bacteria regained all their original fitness. They paid a price for resistance, and then they just evolved their way right out of debt. This whole story, this escape, it really reveals the true nature of the fight we're in against superbugs. This isn't just about chemistry anymore. It is all about evolutionary biology. So the big takeaway here is that this is less like a war we can just win with some single magic bullet drug. It's more like trying to manage a complex, ongoing race against an opponent that is dynamic and is adapting every single second. And as the researchers who did this work put it themselves, these findings just add another layer of complexity to the whole problem. Being able to predict how these vulnerabilities will shift over time is now a critical piece of the puzzle. Which leaves us with the ultimate question, doesn't it? When you're in a race against an adversary that can adapt to every move you make, that can share its winning strategies instantly, and can literally rewrite its own rulebook in a few generations, how do you possibly stay one step ahead?